Hello. In case you've just landed on this video, I must say that this video has a preceding video which is the introductory to the entire concept that we would be dealing with. The link should, of course, be somewhere in the video description. In this video, what I'll be doing is I'll be using the genetic algorithms for solving the problem of trajectory generation for multiple autonomous vehicles. Now, before we select any algorithm to solve any of the problems, it would be nice to see what does the algorithm offer or what does the algorithm does not offer as a principle. The genetic algorithms are definitely optimal when it comes to trajectory planning for autonomous vehicles or mobile robotics. Of course, there's a catch to it that they are only optimal unless the number of turns are really large, which will happen only when there are too many obstacles and you really need to steer through in and around. This does not happen in road scenario. And they face problem in case there are too many narrow corridors, or there's even a single narrow corridor can cause a problem. So if there's a large robot which is initially here, it will face problem in entering situations like this. If these situations don't occur, genetic algorithms are optimal and they are probabilistically complete, which means the probability of generation of an optimal solution or a solution, if it exists, is greater than zero. And that's what normally happens, that the genetic algorithms are able to solve problems and generate a solution reasonably well on time. The big catch that we see in all the algorithms, the iterative algorithms where the solution keeps improving with time, they are definitely better. You get this exciting feature where you can really stop the algorithm anywhere in the process and use the solution. For if it's the problem of motion planning for vehicles, it would be for navigation of the vehicle. If it's for robotics, it will be for the navigation of the robots. You can stop the algorithm at any time and you can use the solution so far. Of course, giving the algorithm more time would have meant a better solution. But then, of course, genetic algorithms are rarely used in real-time operations, in algorithms which are real-time, which is a problem of trajectory generation of autonomous vehicles. The vehicles drive at reasonable speeds, so the planning needs to be really quick. And that is what will be the main area of work in this presentation. The genetic algorithms, like many other algorithms, they are sampling based. So what I do is that I generate in random samples in my workspace, I generate in random samples in my map, and we know that the probability of the randomly generated sample being obstacle free. So in case of mobile robotics, if there's map and there are some obstacle, for such sampling based methods, the probability that the sample is generated in an obstacle free region needs to be high, and therefore I'll be using the road coordinated axis system where the x axis was this axis and the y axis was perpendicular to this axis at any point. The use of this axis system will ensure that every sample that I generate will be within the road. If there are no static obstacles or other vehicles, it will be free. It will be obstacle free, but it will definitely be within the road segment. The other major concept out here is that we know from general robotics that they are path planning algorithms which basically generate a trajectory and require a controller or a trajectory tracking algorithm in order to track the trajectory. So if this is the map, they'll basically generate this kind of trajectory. There may be some obstacles out here, and then a tracking algorithm will track it up. And they are path correcting algorithms. What they do is that as the vehicles move, as the obstacle scenario changes, as some new obstacle come in, as the vehicle, it may slip with time, so it had to be found here, but it's to be found here, so the path has to be accordingly corrected. The path correcting algorithms, they deal with all these kinds of situations. They take in the path which is a result of the path planning algorithm and they keep improving that with time. in literature, mostly the genetic algorithm is used as a path planning algorithm. While we normally do not pay any interest to the path correcting algorithm, we ensure that the controller is good enough to deal with all kind of uncertainties that arise with time. Here we'll be basically in this presentation what I'll be using genetic algorithm for both these tasks. I'll be using genetic algorithm which will perform both the task of path planning, that is the initial trajectory generation for the autonomous vehicles, as well as for the path correction. So all I'll have is that there will be a road like this, there will be some other vehicles or some other obstacle out here, there will be a vehicle to be planned. I will generate a trajectory using the genetic algorithms. The genetic algorithm will keep running. So it's not that once the initial trajectory has been generated, the genetic algorithm will stop. It will continue to run as long as the simulation continues, and at every time step, the genetic algorithm will see what the situation is, and it will correspondingly use the updated scenario of all time for its computation. So if the obstacles change with time, let's say this was a vehicle, it was supposed to be found here and it's now found over here, or the vehicle to be planned, it itself moves. So it was to be found here, but it slipped a certain bit, it skidded a certain bit, it's to be found here. The genetic algorithm will make all these adjustments in itself. So there's a genetic algorithm that is basically always running, that's continuously running, and that sees the scenario. It is able to see the scenario. What we can do is that we can query this genetic algorithm and get the best trajectory so far at any instance of time, and this will be what will be my controller will be based upon. My controller at any instance of time will look at this best trajectory and it will manipulate the vehicle. If the vehicle moves to a new situation, correspondingly genetic algorithm will be able to see that, and it will take the new scenario to modify, to tune, if in case there's any necessity to tune in to further optimize in this trajectory, which gets as an input to my control algorithm. So this is basically planning as you go. As my vehicle moves, the genetic algorithm will keep improving along with time. Now how would be we dealing with the situation of planning of multiple autonomous vehicles using the genetic algorithms? First, I say let us only consider one vehicle, let us forget about all the other vehicles. So first I'll solve the problem using genetic algorithm for a single vehicle. Later on, we'll say that we'll add in more vehicles, and we'll say that how can the algorithm so generated be generalized to multiple vehicles, and there I'll be talking about the aspect of coordination. So throughout this, planning would denote planning for one vehicles and coordination would denote planning for multiple vehicles. So here I'll be dealing with the first part of it, which is only planning of a single autonomous vehicle for a traffic light scenario. Now the underlying algorithm is genetic algorithm, which is a pretty standard algorithm, so there's nothing that I need to do over it. The only thing that I need to say is that in order to solve any problem, may not necessarily be the problem of trajectory planning, in order to solve any problem using the context, using the notion, or using the standard genetic algorithm, there are always three questions that need to be answered. If I'm able to answer those three questions, then the standard problem solving methodology of genetic algorithm continues and the solution gets generated, the problem gets solved. So in the next three slides, I'll be basically solving those three basic questions of problem solving methodology using the genetic algorithm. The first is, what is it that the genetic algorithm is trying to optimize? What is it that the genetic algorithm will try to tune in, to try to change in, to try to move around, to try to play with it? And as it plays along with it, the different solutions get generated. So in our case, the problem of trajectory generation is that the genetic algorithm is to optimize a trajectory which is like this, but trajectory of course has infinitely many points. The genetic algorithm cannot work over so many points, So my problem here is that I need to see what lowest number of points is that the genetic algorithm is trying to optimize. So let us say my solution consists of discretely 1, 2, 3, 4, and 5 points. As I move in these 5 points, the curve will change. The curve, by the way, is produced by a Bezier curve in this situation. The Bezier curve is the same curve that we use for Word. It's a very similar curve that we use for curve drawing and using Microsoft Word and all these programs. It allows you to click and it smoothly joins all the clicked points using a curve. So what my genetic algorithm is trying to do, it's trying to move around all these 1, 2, 3, 4, and 5 points. It'll move around up and bottom. It'll move them around each one of them left and right, and it'll try to see what happens. Can I get a better curve? So these 5 points are the ones which will be optimized using the genetic algorithm. Of course, in general, it is n points. The first point, which will also represents the trajectory, but it's not taken in the genetic algorithm, it is the source. Now you can the trajectory will always start from the initial point of the vehicle, else it's not a valid trajectory. I always start at where I'm currently located. That's then it's when a trajectory is called as a valid trajectory, and it will always end at the goal. So these are the 2 points which are fixed, which cannot be moved. One is the source and the other is the goal, and I already know both of them. My localization systems gives me the initial point, which is the source. The goal is always taken as to be the midpoint of the end of the road segment. So all the trajectories must end out here. There's another simple problem out here is that the vehicles are constrained by the kinematic constraints, or in general the non-holonomic constraints. That is, if a vehicle is standing like this, it cannot trace a trajectory like this. Suddenly it will not rotate in by more than 90 degree and trace this trajectory. So a trajectory generation has to be always initially in the direction of the heading of the vehicle. So there's, besides the source and the goal, the first point I always fix it. This just to ensure that the initial trajectory is generated in this direction, which is again a property of the Bezier curve. The first point gives in the direction in which the trajectory would be generated. So these 3 points are fixed. All the other points are to be optimized. And in problem solving methodology, when using genetic algorithm, what I have is that whenever I know that these are 3 points which need to be moved, which need to be optimized, I always embed them linearly in a individual representation strategy, what is known as a genotype. Each of these points consists of real numbers of the in the x-axis and the y-axis coordinate, or in, because I'm taking the road axis system, the x-axis and the y-axis. So these are two numbers out here, these are two numbers out here, these are two numbers out here, these are two numbers out here. I linearly append them one after the other, and I need to know the limits to all these numbers. So I know that all the x-axis value, they range from 1 to delta. This is what the range is, where delta is the size of the road segment, and y dash value, they range from 0 to 1, because it was taken in as a ratio. So that's the first question that I need to answer. What is being optimized? These 4 or 5 points, or in general n points, are being optimized, and what are they in bounds? The exact values of each of these points ranges from 1 to delta, and the y dash value from 0 to 1. The second thing, or the second question I need to answer in genetic algorithm is, what are the genetic operators, or what are the operators that will work over the solution? And for that, as per the standard methodology, I always have in a crossover operator, which is used for convergence, and mutation operator, which is used for exploitation. This is used for exploration, this is used for exploitation. The only small catch here is that in my individual representation strategy, I said that they could be 1 point, they could be 2 point, they could be 3 points. Now, the number of points I have kept as variable. That means in the same population pool, if one solution has 3 points, the other solution may have 5 points, the other solution may have 10 points, and the other solution may have 0 points. Only the source, the direction maintains points, and the goal. So basically, the one which has 3 points, 3 points means a total of six. 3 points means three x-axis value and three y-axis value. Now this cannot have a normal crossover with something which have 5 points or basically 10 here. They don't have the same size, but I can work over this value nicely. I can take in random for 3 and 5. I can take in any random 2 points here, random 2 points here, make one chromosome out of it, and whatever is left becomes the second chromosome. So that's how this has been handled. It's a crossover between individuals of variable length, and an operator which we do not normally see in the genetic algorithm, which we have added here, is called as the insert. Now remember, it's a problem of optimization for a dynamic fitness landscape, or for a dynamic problem, or a problem where the environment is not static. Now whenever we deal with such kind of problem, suppose there was a road like this, the vehicle was here, let's say there was no obstacle, so the trajectory generated was like this, where this was the goal and this was the source. Suddenly some obstacle comes in, the environment suddenly changes. Now what happens is that all my individual basically would have converged along with time, and they would be representing the same strategy. Now my mutation operator will take a very long time to generate in this strategy. So for such highly dynamic environments, we know, not only for this problem but for any problem, for such highly dynamic environments, what we may sometimes do is that we may add an operator called as insert, which does nothing but adds in random solutions. So let's say at every generation I add in two random solution, which may be a which may be any kind of trajectory, random generated trajectory of the vehicle. So let's say if I add two, one may be this, not a very good looking trajectory, but still better than this, which was completely infeasible, which will make the vehicle move to the obstacle. The other may be a slightly better looking trajectory, this, or let's say this, it does not track to the it does not collide with the obstacle. So I add in random individuals to cope up with such uncertain environments. And the last operator, which is of course the most important operator, which we do not always see in the genetic algorithms. Now one thing which I did not mention when I mentioned the general individual representation strategy, for in mobile robots, if we can be assured that the robot would always be traveling towards the goal, so it can travel in like this, it can travel in like this, but it can never travel using a path with the projection of which is behind the, is not in line connecting the source and the goal, so it's basically going behind. And that's sometimes a valid assumption even to make in mobile robotics, that the robot will never go behind, and that holds for most simple obstacle. Of course it does not hold for obstacles like this, where the robot will have to go behind in order to reach the goal. For road like scenarios, we always see that the vehicle will never have to turn behind and then again come. No matter what be the obstacle scenario, it never happens. The vehicle never has to go behind. The vehicle always drives forward, be it driving like this, be it driving like this, or be it driving like this. It will always drive forward. What it means is that I can add one constraint in my individual representation strategy, is that all the points would be taken in increasing order of the x-axis value, which means if this is a road, I can never take an individual representation strategy where there is of course the source and the direction maintenance point. I can never take a strategy where this is the first point, this is the second point, and this is the third point. I'll always have to take this as the first, this as the second, this as the third, because this trajectory is bad and this is good. So my points are always sorted in terms of the x-axis. This helps a lot. this helps a lot. This constraint helps in a lot. There's another thing which is which I carry forward straight from mobile robotics into vehicles. When it comes to mobile robotics, every deletion in general optimization, we never use anything called as deleting something from the individual or deleting variables, which by the way is not even allowed. But in mobile robots, what happens if this is a simple obstacle and my planner found a trajectory like this? It's clearly a very bad trajectory. Every time I delete a point, every time I delete one point, the trajectory gets shorter. And if it's still feasible, if it's shorter and better, then I can get a great benefit from it. My algorithm will perform much faster. So in this mobile robotic scenario, if I delete this point, I'll basically get in this much shorter and much better trajectory. If I delete this point out here, I'll get a much better and a much shorter trajectory. And if I delete this point out here, I'll get a much shorter and much better trajectory. So a very bad looking trajectory, I have basically been able to transform into a very good looking trajectory and a much better trajectory, which is this. I started out with a very bad trajectory and I smoothed it to a very good trajectory only by deletion of points. So deletion is a very good thing to do in mobile robotics, and the same in a vehicle scenario. If my trajectory is anything to do with like this, it's that odd, I can delete this point, 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 and making a very good trajectory like this. As long as it's feasible, as long as it is better. So that is what one thing that we do. We delete in operators, and not to mention that every point in either mobile robotics or in autonomous vehicles, it denotes a turn. It denotes a steering, a major steering event. It And if I delete points, my turns get reduced, my steering gets reduced, which means a much straighter drive. And the third and the last question, always to answer, always to ask in the use of genetic algorithm for any problem, is the fitness function of what is being optimized. Or if I have 10 different trajectories, how to assign a goodness cost or some goodness or quality measure to each of these trajectory. So here it's simply the length. What I do is that I basically trying to find out the shortest trajectory, the shortest length trajectory. My genetic algorithm would generate in random solutions, or let's say that it's not assured that every trajectory will pass through an obstacle free region. So I need to heavily penalize the trajectory which is passing through an infeasible region. And in robotics, we know that we minimizing the length will usually mean that the trajectory just kisses the obstacle and moves. So it's very close to the obstacle and move, which is very dangerous. I always need some safety distance, and hence this trajectory is much better because it considers nice safety distances from both the road boundary and the obstacle. So if the vehicle is not maintaining a safety distance, I again penalize it. So what's my total cost function? It is the length of this trajectory. If a part of it is inside the obstacle, then and this is the length, then I add a penalty of alpha times L. And if there is a part of trajectory which is not maintaining the safety distance, let's say this much is not maintaining safety distance L2, then beta L2 will be the second penalty I add for safety distance, and of course alpha is greater than beta. The penalties are always larger, which by the way is greater than 1. So basically I've answered those 3 questions. I've seen how the individual representation strategy would be, what would be the genetic operators, and what would be the fitness function. So now the conventional genetic algorithm, the very simple genetic algorithm, can be used to solve the entire problem. It'll go exactly as the genetic algorithm would do. Now one thing here is that the genetic algorithms of course are time complex. They take in a lot of time, and where the most of the time is wasted, it's wasted in the fitness evaluation. the fitness function cost, so I just told that it needs to find out which part of the trajectory is feasible and which of the part of the trajectory is without safety distance. And how do I do that? I check in point by point. From one point to the other point, I check in which part of the trajectory is feasible, which is not feasible, which is feasible, which is not feasible. This is the only step in genetic algorithm which takes time, the fitness evaluation. So if I instead say that I'll check in the first point, I'll check in this point, I'll check in this point, I'll check in this point, and I'll check in this point, it gets boosted by a great factor. You can see that so many points are being missed, and that's why the algorithm performance gets boosted up. Unfortunately, the problem that it gets is that I now no longer have a clear idea of which part of the trajectory is feasible and which is not feasible. There may be a slight obstacle out over here, and because I checked this point and this point, I did not check in this point, I completely overlooked it. An infeasible trajectory is now called as feasible. In normal methodology, if I would have been solving for mobile robotics, what I would have done is that at the initial few generation, I would have checked at a coarser resolution. I would have checked in like this, and at higher generation, I would have checked at each and every point. In vehicles, what I'm doing is that I know this part of the trajectory can be optimized later on when the vehicle is, say, roundabout here. At that point, I can optimize the later part of the trajectory, but this part of trajectory is used for the immediate movement of the vehicle. So I'll check in every point at the start, and as we move later on, I'll check in for at points which are well far apart. So even if it's there's an obstacle here and the trajectory being followed is actually obstacle prone, when the vehicle will reach here, then it'll nicely check in for this obstacle, it'll find this obstacle, and it'll take a alternative path. So my granularity of checking, it is finer at the start and it is coarser at the end. And there are some amazing things. This figure was only used to illustrate that these, if you take the entire map as a mobile robotics map, it gets very difficult to solve these kinds of optimization problem, because I'm taking a road coordinate axis system. Such problems can be solved in virtually no time. So that was the first part of the problem, where I said that first I'll be assuming that there are no other vehicles, there's only a single vehicle. I'll be dealing with the problem of trajectory generation for a single vehicle. Now I move on to the other part, which says that of course there are so many vehicles on road. Here we'll be assuming that all of them are connected by a communication framework, so they can all communicate to each other. And based on that, I'll be generalizing the problem to multi-vehicle. So for the problem of coordination, the general principle used is called as a priority based coordination, which means if you are given in mobile robotics, if you are given a map, there are 3 robots out here. First, forget about both these robots, only consider this robot. Suppose it needs to reach this, generate in a trajectory like this. In the second step, forget about this robot, only consider this robot. Suppose it needs to move like this, make it navigate through this point, but ensure that you do not collide with this robot. Since we know the trajectory of this robot, then this robot can be simply taken as a normal obstacle which is moving. The complete trajectory, the complete dynamics is known. So this robot can easily ensure how to avoid this robot. And the third would be this robot, wherein it will have to move to a point, say here, ensuring that it does not collide with this robot moving with this trajectory and this robot moving with this trajectory. Of course, both the robots and the exact trajectories are known, so we can easily take it as a obstacle which changes with time and say this was the path. So this is priority 1, the highest priority robot. This is priority 2, the mediate priority robot, and this is priority 3, the lowest priority robots. And we always have to fix the priorities. In a road scenario, I take in the same thing, where if there is one vehicle like this moving ahead, there's second vehicle like this moving ahead, there's a third vehicle like this moving, say, this side. Here, the highest vehicle has the highest priority. The vehicle which is most distant in terms of the x-axis has the highest priority. The vehicle ahead has highest priority, and we do it for a simple reason. While driving, we really do not care of how the people behind us are driving. What are they trying to do? What are they trying to achieve? We care about what the how the people ahead of us are achieving. If two vehicles collide, it's always the fault of the vehicle behind who did not account for the vehicle in front. So this vehicle will not consider this vehicle in its planning. This vehicle will not consider this vehicle in its planning. It's ahead. This vehicle will consider both this vehicle and this vehicle in its planning. It's behind. In general, I can say a vehicle more ahead in the road has higher priority to a vehicle more behind, and only the vehicles ahead are being considered. So anyway, this vehicle will not consider any vehicle which might lie behind it. Now, when I had a single vehicle, the task was very simple. I simply had embedded all the points into a genetic algorithm framework, and those paths could be traced with the any velocity, or let's say the highest possible velocity which the control algorithm can manage. It does not matter at which velocity do I navigate this point. But for multi robotics, what happens that the trajectory of one vehicle is dependent upon the speed by which it travels. And a very simple example would be that if I, in robotics, if I have one robot out here and another robot out here, say this is traveling in this direction using this trajectory. If this is very fast, if the second robot is very fast, it can nicely reach this point using this trajectory. But if it is slow, it might have to wait for this robot to pass away first and then go away. Alternatively, it will have to change its trajectory to something like this or something like this. So the optimal trajectories are speed dependent. One way to handle this would be that whenever we cannot think of something, we say that let's embed everything into the genetic algorithm framework and it will do its job. So it will not only optimize the path, it will also optimize the speed. It will not only optimize the points, it will also optimize the speed associate the speed of driving at those points. But this makes the genetic algorithm problem optimization problem very large, so I do not do that. Instead, I frame in a very simple control rule out here. I frame in a very simple rule out here, wherein I just say that if my genetic algorithm at any instance of time is able to generate a feasible trajectory, I'll try to increase its speed. And I must say that if my genetic algorithm is able to compute a trajectory which is safe as well as it has safety distances associated with them, I'll increase my speed. If it cannot, if there seems to be a collision, I'll obviously stop. I'll decrease my speed by a fixed amount. If the safety distances seem not to occur, I'll again decrease my speed. So this continuous cycle of the genetic algorithm optimizing the path based on which based on the path the new speed is find out, it's either increase or decrease. Based on new speed, again the path is find out. Based on the new path, again the speed is increased or decreased. This keeps on happening in cycle, and what will practically happen is that suppose the vehicle was initially traveling straight, it's at very high speed, it suddenly observes a new obstacle, and the genetic algorithm nicely sees this obstacle and modifies the trajectory to this. Let's say the road was only this much. Now it cannot travel. Now the safety distance which existed before it was traveling in the entire road, so it was a very wide safety distance. Now the safety distance is less. In our methodology, the safety distance is proportional to the speed. So now it's not getting the safety distance, so it will keep on saying the because it does not get the safety distance, it will reduce its speed, and that's what practically how we drive. We see an obstacle, we reduce the speed. It will reduce the speed which is safe enough to navigate this small region out here. Once we have got a speed which is considered safe enough as per this low safety distance, then there's no use of further decreasing the speed. So I'll basically drive at a constant value. Increase in speed is not possible because increasing speed will increase the necessary safety distance, which will make the path infeasible. And decreasing speed is not possible because if we decrease the speed at the next instance, I see that the path is feasible, safety distance is available, so I should increase the speed. So it'll decrease the speed and it'll travel at a constant speed. After the vehicle reaches this point, it'll see that a lot of safety distance is available. It'll start increasing the speed again. So that's how I handle the problem of speed optimization, which is a problem only in the case of multiple robots or multiple vehicles. Now I said that the general philosophy is of a priority based coordination, which is unfortunately non cooperative in nature. So if I have got a road like this, I have got a vehicle here, I've got a vehicle here, let's take the same scenario. This vehicle, and let us say the road was not that large, the road was only like this, and this vehicle was quite big, it was like this. Now this vehicle wants to overtake this vehicle, but this distance is small, this distance is small, the vehicle cannot fit in any of these distance. This vehicle is of course traveling straight. It sees the vehicle behind, but it's not since it is a vehicle much ahead. In priority based coordination, a higher priority vehicle does not consider a lower priority vehicle in its planning, or this vehicle which is ahead and has higher priority does not consider this vehicle in its planning. So what happens? This vehicle has nothing to do, but it will keep reducing its speed and ultimately it will have to follow it. There's nothing that this vehicle can do. And clearly we see there's a very simple way in which overtaking is possible, in which the vehicle behind, which is capable of higher traveling speed, can overtake the vehicle. If this moves slightly like this and it occupies this position, then this vehicle has got sufficient distance to overtake this vehicle, and this is beneficial for both. Now remember, one of my basic objective behind the entire research is that any feasible overtake should be feasible, and this is what in general what I always mean by cooperation. Now priority based coordination by principality it is not cooperative in nature, so I'll have to do something in order to make it cooperative in nature. And how do I do that? So far whatever I have presented the entire architecture of the problem, it did not cater to this need of cooperation. So first thing that I'll have to do is that I'll have to embed a framework, I'll have to embed some variables, I'll have to embed in something where heuristics can be added. I'll have to change the very framework of the algorithm so that there's something that the heuristics can control. Heuristics, by the way, are rules of thumb. They are like the principles, they are like the logic associated with something. So I'll have to add in some new variables, something in the problem framework in order to what the heuristics can exploit. And that is what I do here. I make in a very simple change in the framework that I have been presenting so far. I say that there's a new feature added where any vehicle can request any other vehicle to do something, and this something can be either a change in its steering, either it can request it to turn slightly left or turn slightly right. This is the first request which can come from one vehicle to another vehicle. The second request which can come from one vehicle to another vehicle is to change its speed. So if this is the vehicle behind and this is the vehicle front, this vehicle can request this vehicle to increase its speed or decrease its speed by some amount. If it does so, the normal speed change mechanism that this vehicle was following will get overridden. That's a very simple way in which I have changed the framework, that in place of the normal way in which this vehicle was deciding its speed, in place of that it will consider the speed requested by this vehicle. So that is one way in by overriding one thing in the special case of a request, I've created some mechanism in which heuristics can be added. The second way is by turning right or by turning left. If this vehicle requests a left turn to this vehicle, all it does is that there was a source, there was a directional maintenance point. I'll turn the directional maintenance point slightly on the left or slightly on the right. So the initial trajectory will take in a slight dip left or a slight dip right. So basically there are two kind of framework changes that I have made only to enable me embed some heuristics, only to create a framework in which heuristics can be embedded. One is the speed change mechanism, where I say that in when requested, the speed change mechanism gets overridden by the requested speed change. And the second mechanism was that the direction maintenance points, it gets tilted a little left, a little right to produce a little clockwise steering effect or a little anti-clockwise steering effect. Of course, every request may not be granted. It's possible that this vehicle requests this vehicle to do something and it does not do so, what we would be seeing later on. So there are basically two heuristics that I would be following. They are the heuristics here from now on would only be scenarios. There would be two special scenarios that I would be considering, which enable me to decide whether a vehicle should request in a vehicle to speed up, speed down, or turn right, turn left. That's all. Now heuristics has a control rather than control points. That is what the heuristics would be doing. It will be deciding whether a vehicle asks requests another vehicle to do something or not. Now the special scenario is that I have got two vehicles. I basically consider two vehicles out of many vehicles out here. This will either be following this vehicle or this will be overtaking this vehicle, whatever the case may be. If it decides to follow this vehicle, in future it must always be ready to complete an overtake whenever overtake becomes feasible. If it decides to overtake, it must always ensure that overtake is feasible. Many times what it can happen, even in practical driving, we decide to overtake, we take in an overtaking trajectory, we continue the overtake, but later on something happens that the overtake cannot be completed and we need to make in a very awkward decision. Say suddenly something come up over here and the vehicle is here, so it will have to make in a very awkward decision of steering left and ultimately avoiding collision. So while we are overtaking, we need to always ensure whether overtake is still feasible, and when we are following another vehicle, we always need to make sure whether it is now possible to overtake, which was initially impossible. And in both cases, we'll see how the trajectories, how the request can be made. So from now on, I'll give in scenarios and I'll basically look into in what request should be given. So this is the first scenario. This is scenario 1, wherein I say that there was the vehicle behind could construct in a good overtaking trajectory. It seems fair enough. There's nothing wrong in this trajectory. It should be the trajectory is safe. The safety distance are always maintained. So what should be done? Now clearly we know that the trajectory can be made better if this turns left and this turns left, and that is exactly what is the request that is broadcasted. These two turn left, and in this case it so happened that it was possible and these two vehicles did cater to the need. They turned left. Subsequently what happened that this vehicle is still ahead of this vehicle, and therefore it makes sense to further this vehicle, to request this vehicle to further move left. But what will happen when it's at this point? Further turning left is not possible. It will try to turn left, it will find the infeasible path, and then when it finds an infeasible path or a path in which the safety distance cannot be maintained, then it will simply cancel the request. It will say that the request cannot be granted because because it breaches with the safety distance or it breaches with the feasibility. This vehicle can still, even at this position, this vehicle can still turn a little more towards the left. The more this vehicle moves out here and the more this vehicle moves out here, the straighter this trajectory gets. That's why it's asking these two to turn left. And in normal overtaking, that is what we see, that this vehicle will ultimately keep pushing both these vehicles aside the maximum that they can do, and it will come up with a very straight looking trajectory which is out here, and it will ultimately complete the overtaking. However, what can happen is that the three vehicles computed their trajectory at some point of time. Let's say the overtaking have initiated the way it initiated in the previous slide. This is the second scenario. This vehicle initiated the overtake, but now what it finds is that this is the trajectory of this vehicle, this is the trajectory of planned trajectory of this vehicle, and this is obviously these two have cooperated much. They have come up the most side they can, and hence this trajectory is almost very straight and very smooth and very nice for this vehicle to complete the overtake. However, it sees that when this vehicle will be at this position like this vehicle would be at this position like this, and the two will have too close a distance, so the safety distance is not being maintained. The trajectories would still be safe in the sense that the trajectory would still be feasible in the sense that there will be not collision, but the two vehicles would have come very close to each other, and in overtaking we do not want this to happen. Two vehicles coming very close to each other, there's a threat, there's a risk that collision might happen. It might just happens. So now the problem is that these two vehicles in future course of action are coming very close to each other. What is it that I can do that they do not come that close to each other? What is it? How is it that I can change in the that I can cause some kind of change? And the very simple request is that if R2 is asked to be slow, if this vehicle slows down, then it will be very easier for this vehicle. It will simply follow through. When this vehicle is again at this position, R2 would have moved very little. It will be at this position, and hence this separation would increase. The diagram is not very good, but you can practically imagine that if you, while overtaking, you are coming very close to a vehicle, if that vehicle slows down, the overtake becomes much better, it becomes much more safer, and that's what happens. You many times you see people at site overtaking you, and you can risk that there's some threat, you just slow down as a mark of cooperation to the other vehicle. You just slow down, which makes overtaking feasible. Similarly, if this distance is small between R2 and R3, between these set of vehicles, when this is found to be found here, this is to be found here, and the distance are very less, R3 slows down. When the overtake is completely infeasible, it can be seen that these two vehicles, as per their planned trajectories, they are colliding. If that is the case, then the overtake is cancelled. Or if these two are colliding, overtake is cancelled. The problem is that reducing the speed of R2 or R3 might still make overtake feasible. If they slow down very much, it might even make the safety distances enough for overtake to be feasible and ultimately completed, but there's a lot of risk associated with it, so we say that we do not take that risk, we completely cancel the overtake. So abandon, and when it abandons, of course there is no request issue from any vehicle to the any other vehicle. It will simply try to construct in safe trajectory, which means keep on reducing your speed until you start following R2, or until later something happens and the overtake magically becomes feasible later on. So that was the first heuristics, and we saw that how the heuristics was this was the way, this was these were the scenarios happening in these were the scenarios that were practically happening, and the heuristics was in the form of these requests going from one vehicle to other vehicle. The similar is the vehicle following heuristics, where say one vehicle is completely unable to construct a feasible trajectory on, or an overtaking trajectory. The overtake is not possible because these two vehicles are very close. So now what this vehicle does is that it tries its best to be prepared for overtake, even though it does not overtake. So it still requests these two vehicles to move in their left side so that overtaking later on can take place as soon as possible, which is the typical weaving behavior associated with driving. You try to gesture all the way that I want to overtake you as soon as possible, I want to overtake at you. So there's a request to move left, there's a request to move left for both these vehicles. Because this trajectory is infeasible, the vehicle is traveling at a very high speed, it'll R1 will itself have to slow down. In fact, the normal speed change mechanism, not the overridden one, the normal one will do that. Because the trajectories are infeasible, it will slow down, and ultimately it will be nearly following this vehicle, try to push both these vehicles up and until this vehicle leaves. Now it can construct a nice trajectory. Of course, this trajectory is not nice. R1 is directly behind R2. It will request R2 to be as left as possible, so that the trajectory can be made very smooth. It can be made as smooth as possible. In this case, there is no scope for R2 to left, because R2 has already gone in as left as possible in the preceding steps. So R1 simply follows this overtaking trajectory and ultimately completes the overtake. So these are two heuristics to follow. Of course, when you consider the actual diagrams and these figures, it becomes difficult to understand. But in all cases, all you need to consider is that, suppose you had the power to talk to the other person while following him or while overtaking him, what would you have told him or her? To slow down or to turn in a particular side in order to make overtaking possible? In our algorithm, this communication exists. This is actually possible, and we actually request this to the other person. And how these requests are catered is in the changed framework that I have produced for the modified genetic algorithm. The only thing in this complete diagram, which is the overall diagram, that I have not considered is that thing that when for some consecutive generations I am not able, the genetic algorithm cannot find a feasible plan. It slowed down, it could not find a feasible plan for some number of generations. It means that the road is blocked. The indication is clear. And the road is blocked, that means we need to use the overall route planning algorithm, which is the Dijkstra's algorithm taken in the introduction. Again, we need to recall it and we need to select a new route to the destination. Of course, it's a very preliminary way of handling blockage, and we need to go by this new route, because the route we are going is block, and blockage simply means that this is the vehicle and this complete road is blocked, so there's no feasible trajectory from one side to the other side. And these are the results for the overall algorithm. This is a road network graph. The vehicle nicely comes in. If it detects a blockage, it changes its route. A vehicle traveling here, they can all avoid each other. This is the case of overtaking, where this vehicle came in here and it overtook the first vehicle. And this this is entirely driven by the heuristics that I presented along with the modified genetic algorithm. The first was the overtake behavior, and the second is the vehicle following overtake. See, when this vehicle passed, this could now overtake the red vehicle. The green vehicle could overtake the red vehicle after this vehicle passed, which is very obvious. It was completely waiting for the vehicle to pass. And these are some analysis. If I increase my speed, I'll need more safety distance, so my total distance of travel would obviously increase. I'll have to keep in greater gap with the obstacles and this thing. And if I increase my speed, I'll naturally take lesser amount of time to reach my destination. That's why people travel more. With genetic algorithms and any kind of evolutionary technique, one thing that we need to always do is that we need to say that how increasing the total population size, it'll enable better and better optimization. Of course, increasing the number of individual or increasing the population size also means increasing the time of optimization. This is for theoretical reasons we need to show this graph. And similarly, for theoretical reasons, we need to show this graph, that what is the scalability with respect to the number of obstacles. So if I keep adding obstacles on my road, it'll take more and more number of solution to generate a basic feasible solution, which at least a trajectory, it's not the optimal solution, it's a feasible solution. And we know once we have a feasible solution, it takes very less time to optimize it. So this is how the algorithm scales to increasing the number of obstacles. And that's all for the algorithm. Thank you.